Okay, this is the recorded lecture for Chapter 3, Part 1 of your notes. And you can see that in Chapter 3, we're going to learn a little more about motion. So basically, what do we mean by explaining motion? You might think motion just happens, right? Well, when you're speaking in the physics worldview, to explain something means to create a scheme, a model, excuse me, that can predict the outcome of experiments. So physicists try to create a set of ideas that explain how the world might work. Motion appears to be reproducible. That is, if we start out with the same conditions, do the same thing to an object, we get the same resulting motion. So this reproducibility is a necessary condition for even attempting to search for a set of rules that nature obeys. So, what is motion of an object when there's nothing external to change its motion? So if you do a simple experiment, you have a book on the table and you give it a brief push across the table. What happens? Well, you notice that the book starts in a straight line at some particular speed and it quickly slows down and stops. So it seems natural for an object to come to a rest and remain at a rest. So remaining at a rest is what we consider a natural state. Now, if you do that same experiment with the book, but now you have a surface that's covered with ice, the book is going to go a greater distance before coming to a rest. So the explanation of these two different results is that one, basically different surfaces interact with the book differently. On a surface that's slick, the book would not slow down at all. It would continue in a straight line at a constant speed forever. And so if you state that a little differently, when the interaction is reduced to zero, the book's motion is constant. It seems that a natural motion is one in which the speed and direction are constant. So an interaction with an external agent is required to cause an object to change its velocity. If you leave it alone, it would naturally continue in its initial direction with its initial speed. Now, Galileo did a lot of what's known as thought experiments. So basically, he would think of a concept, think of an experiment. So he thought about the motion of a round ball. What would happen if he put it on a tilted surface free of all external and accidental objects? So you can see in the picture we have a inclined surface. We're going to put the ball at top. And he said, well, the ball is going to roll down the slope and it's going to speed up. So if the ball goes the opposite way, in that if you push the ball up the slope, it's going to slow down. So then Galileo asked himself, well, what's going to happen if I put the ball on a level surface? Nothing. Because the surface does not slope, so the ball is not going to speed up or slow down. The ball is going to continue in its motion forever if you assume there's no resistive interactions between the ball and the surface. So what do we mean by no resistive interactions? Basically, no friction. So Galileo was the first to suggest that a constant speed, straight line motion was just as natural as an at-rest motion. The property of remaining at rest or continuing to move in a straight line at a constant speed is what we call inertia. Now, typically, commonly when you think of the word inertia, it usually talks about your emotional state. You're feeling tired, you're feeling sluggish. Common use of the word inertia, it's hard to get moving. I can't get up to get going. Now, I'm sure a lot of you have seen the experiment like shown in these pictures where there's a table set and the person yanks the tablecloth. Okay? Well, so the dishes are at rest. They have to have an interaction to get them moving. So you get this magician. He's using the property of inertia of the cups and the saucers when he abruptly pulls the tablecloth from beneath them. If your tablecloth is smooth enough, the interaction is going to be very small and the dishes are going to remain nearly at rest. So there's really no magic behind it. It's all physics. But if there's more to inertia, there is more to inertia than getting things moving. If something's already moving, it's difficult to slow it down or speed it up. A good example would be seat belts. So your seat belts are basically counteracting your body's inertial tendency to continue forward at a constant speed when your car suddenly stops, when you slam on the brakes. Now keep in mind, all objects do not have the same inertia. So we're going to go into Newton's 3 laws. And Newton's first law, so basically you have Isaac Newton, and he did a lot of work like Galileo did. He was very interested in interactions, and he was interested in those interactions that occur while that object is in motion rather than the final destination. So Isaac Newton formulated Galileo's observation into what we now know as Newton's first law. Newton's first law is also referred to as the law of inertia. So stated, Newton's first law says the velocity of an object remains constant unless an unbalanced force acts on the object. Now, for the velocity of an object to remain constant, the speed and the direction must both remain constant. So speed has to remain constant, direction, both of them have to remain constant. So the law applies to the special case of an object at rest. An object at rest remains at rest unless acted on by an unbalanced force. So Newton's first law incorporates Galileo's idea of inertia, and it also introduced this new concept that we call force. So basically, there's no acceleration unless there's a net unbalanced force. So the concept of force includes a lot more than what we think about it, simply a push and a pull. Force can be defined in terms of the observed behavior of objects. Forces are directional. And what that means is that direction of the force is as important as its size, because different results are going to be produced by forces of the same size when applied in different directions. But if you have two forces of equal size acting along a straight line but in opposite direction, they're going to cancel each other out. So the forces tend to stretch or compress the object, but the unbalanced or net force is zero when they cancel each other out. So imagine there's a skater, and that skater's coasting across the ice. A force in the direction of the original motion increases the skater's speed. A force in the opposite direction will slow the skater. So we need to incorporate this difference into our understanding of motion. And the way we do it is by treating forces as a vector. Now, if you remember, we've talked about the differences between vector and scalar quantities. Vector quantities are described by both magnitude as well as direction. Scalar quantities, remember, are just described by magnitude. Direction isn't important. So when you observe an object with no acceleration, you can infer that there is no unbalanced force on that object. If you see a car moving at a constant speed on a level straight highway, you infer that the frictional forces balance the driving forces. Okay, so we're not saying there's no forces acting on the car because there are a lot of different forces. But the main crucial point is that the sum of all these forces are zero. So there's no unbalanced or net force acting on the car. Okay, so an unbalanced force, the sum of the net forces is not zero. So what about this little question? What is the net force acting on an airplane in level flight flying at 500 miles per hour due east? Well, the key to this problem is saying it's level flight. Okay. And it's 500 miles per hour due east. So the speed's not changing, the direction's not changing. So there's no acceleration. So therefore, your net force must be zero. Now, what about this one? If Bob's pushing a heavy couch to another part of the living room, Bob is pushing with a force of 10 newtons, while the couch is pushing against Bob with a force of 8 newtons. So we have 2 newtons. So in this case, your forces are unbalanced. So the couch is going to move in the same direction that Bob's pushing it because Bob is pushing with a greater force than the couch is pushing back at him. Now, we know vectors have direction and magnitude. Okay, there are certain rules for combining vector quantities. Displacements, velocity, accelerations, forces. The way we know we have a vector quantity is the length represents the magnitude of the quantity, and its direction represents the direction of the quantity. When you're writing vector quantities, you usually have, like you see here, a bold face, or you have an arrow over it. Notice right here, we have a capital F with an arrow. Okay. Notice the arrow is pointing toward the right, and your arrow will always point toward the right, regardless of the direction the force is acting. And notice we have kind of an italics symbol that is very common for forces. So let's do an example where we're adding vectors together. So we're walking a distance of 80 meters due north. So this first line with arrows is 80 meters due north. Okay. And you can see we have a scale that shows us the displacement. So now we're walking 80 meters due north, and we stop, which is we're stopping right here, but then we're continuing to walk another 60 meters. So my total displacement is going to be the 60 meters plus the 80 meters. Let's write that a little better. So my total displacement is going to be my 60 meters plus my 80 meters, which gives me a total of 140 meters. And my arrows are showing I'm going up or to the north. Now, what happens if we say we're walking 80 meters due north, but then notice we've now turned around and we've walked 60 meters due south. So what's your displacement? Well, your displacement is going to be this right here, which is your 20 meters, which is your 80 meters minus your 60 meters, which gives you your 20 meters. Okay, and it would be to the north. Now another example would be in this one. We're walking 80 meters due north, but we're going to turn right, as you see in this picture, and walk 60 meters due east. So to find your displacement, you are going to draw an arrow from the beginning, right here, to the end, and you can see we connect it. This is a right triangle, so you're basically finding the hypotenuse of the right triangle. Okay. If you wanted to find the angle, you could use a protractor. We're not going to be dealing with any angles. We're just going to be adding and subtracting vectors. And remember to get, if we say 80 was A, 60 was B, 100 was C, remember A squared plus B squared equals C squared. So 80 meters squared, 80 meters squared plus 60 meters squared, that's going to equal the 100 meters. Now, there is a method to adding vectors, and we call it the tip to tail. And this tactic box shows you how to do it. So we have two vectors. We have A and B. So what you want to do is first you're going to draw A. So you actually have to redraw A and B, keeping them in the same orientation. So notice this first picture, we've taken A and we've redrawn it. And then we're going to place the tail of B at the tip of A, keeping B oriented like it was initially. And then we're going to draw an arrow from the tail of A to the tip of B, and that is our A plus B. So the key is to make sure you keep the original orientation of A and B consistent when you redraw them. So let's look at this example. So here I've given you two vectors, P and Q, and I've asked you to determine what of these vectors, A, B, C, or D, best represents the vector P and Q. So remember, we have to redraw them. So the first thing we're going to do is redraw P. So, and I mean, we're just going to kind of eyeball it. If you have a ruler, you could use that ruler. So that's going to be our P. our Q kind of goes like this. Okay. So we've placed the tail of our tail of P to the tip of Q, which, if you notice, I drew it wrong because I put the tail of Q to the tip of P. So let's fix that. Okay, so I'm going to redraw P. Okay, and the next thing I'm going to do is place the tail of Q at the tip of P. So I'm going to do something like this is the tip of P. So let's see. I'll do something kind of like this. So this is going to be Q. And then I'm going to draw from the tail of A to the tip, tail of P to the tip of Q, which is going to be this. So that's going to be P plus Q, which in this instance, our correct answer is A. So it can be a little confusing, but after practice, it will come naturally to you. Okay? Just always go back and remember those 3 steps that I've given you. Now, in this one, we have a woman that walks 4 kilometers to the east. So here's where we're starting, right here. Okay? We're going to walk 4 kilometers to the east. And then we're going to walk 8 kilometers to the north. And like I said before, this is not to scale. And we want to know the displacement. Okay? So let's say R is what we want to know. So we know that R squared equals 4 kilometers squared plus 8 kilometers squared. And then we know that R is going to be the square root of 4 kilometers squared plus 8 kilometers squared. So that's going to give us R equal to 8.94 kilometers. Okay, this ends the recording of the notes for Chapter 3, Part 1.